the end in a sense. I'll talk about two concrete applications that might justifiably be called text mining. But in order to get there, we'll have to cover some preliminaries. So mostly having to do with some kind of pre-processing. So that's what I guess we probably end up spending about the time on pre-processing and the rest of it on two actual text mining applications. And you'll hear more concrete applications in the course of the next 3 days. Maybe it's best to start with the school textbook style definition of what text mining is. And depending on where you're coming from, you could either work with a strict definition or a loose definition. So the loose definition would be anything that you do to extract useful information from textual data. Something like traditional web searching, where you have some kind of an information need and you want the search engine to find relevant web pages for you. Loose definition, that would count as mining. If you're stricter in your definition, then you want the extraction of information that was previously unknown. Naturally, potentially useful, but the information has to be implicit. It's not enough just to find a web page that you might find useful for a you actually have to synthesize something that wasn't already explicitly so in this case, like I said, you'd have to create something that did not already exist, and it wouldn't be sufficient just to find an existing web page in response to an information. So what we'll do is, I think, as far as the applications are concerned, I probably think that they would follow the, I mean, they fall within text mining even according to the strict definition. But the pre-processing that we'll talk about would be useful in either case. So this is probably text mining itself, probably a buzzword that's been around for what, about 10 years now. So if you look at what text mining is, it draws on techniques and ideas from various disciplines, and all of them are fairly traditional. So if you look at the topics that are listed there, statistics, artificial intelligence, information retrieval, so it's mostly a kind of interdisciplinary subject. So some people, I mean, if you're not feeling too charitable, you might call it old wine in a new bottle. But even though, I mean, any of information retrieval, statistics, or artificial intelligence is at least 50 years old. So what's kind of hot about finding why is it so interesting all of a sudden over the last several years? I guess primarily because we have now much more textual information readily available than we had earlier. So prior to the web, which happened about 94 or so, most of kind of large collections of text were of them, and pretty much anything that you see that has to do with the web has a fairly strong commercial component to it. So I don't think I'll have time to talk about this much, but remember I just talked about information retrieval, so that has its origins in the libraries. And the way it used to be done, actually when the first web search engines were built, so think of Alta Vista and such, when the first web search engines were built, naturally they kind of borrowed the ideas that had traditionally been used from information retrieval. But found soon enough that because of the commercial interests involved, traditional techniques that work well on a static collection didn't work well on the web. One of the reasons was because people, there were commercial incentives associated with getting traffic to your website. So, in contrast to a library setting, where librarians catalog entries, so you can assume that the catalog entry is a truthful representation of a particular item. On the web, what people say about themselves is no longer very reliable. You might represent your own content in order to kind of get traffic that you would not otherwise get. Why? Because that translates to financial benefits. So basically, because okay. So what's the lesson learned? The lesson learned is that traditional techniques that work very well in a library setting or for static collection fail miserably when you apply it on the web. So I mean, the e-commerce potential, you can look at it positively in the sense that text mining tools would be useful for businesses that want to find interesting patterns in their textual data. But it also, I mean, because of the financial aspects involved, it throws up a new set of challenges. So, like I said, I probably won't have time to talk too much about the difference between traditional IR techniques and how the advent of the web changed that. So, what you see in Google is very different from what was there in the early search engines. So that has, I guess, more to do with mining the structure of the web rather than mining the content of the web. It's kind of slightly tangentially related to our subject of discussion today. So what I'll do now is first look at the scope of what we're trying to do. So I've just said what I'm not going to talk about, which is kind of, I'm not going to talk about link mining and such. So what is it that we're trying to mine? So of course, I mean, I've already talked about the World Wide Web, and it's worth kind of thinking about this in slightly more detail. Specifically, what kinds of content on the web are we looking at? So part of it is kind of the traditional web, the way it's been for the last 20 years or so. So that's kind of static web pages, mostly having unstructured text. You also have some semi-structured text, and I think that kind of ties in fairly well with what's traditionally called the deep web. So what's the deep web? Basically, it's kind of, okay, if I say it's not stuff that's available on the surface, that's not saying very much, but basically the idea is, remember earlier I called the pages static, so they exist at all times. The deep web consists of dynamic pages that don't exist per se, but are kind of manufactured or created on the fly in response to some kind of a query submitted by a user. Very often, these deep web pages, because they are kind of one typical way in which pages on the deep web are produced, is you have a database containing some information, and in response to a user query, some information is fetched from the database and displayed to the user in the form of a web. So information like this tends to be either fairly well structured or semi-structured. Generally slightly easier to handle than completely unstructured free-flowing data. And say over the last few years, there's a lot of material available on various social network sites as well. So this is probably the most familiar kind of text that you think of. But apart from the World Wide Web or the internet, as you would call it, there's also the intranet. So companies which have kind of opted for an electronic workflow probably have large quantities of electronic text in the form of things like internal correspondence, email, memos, technical reports. Plus, if you have a kind of explicit customer interface, then you probably have email from customers, customer forums, reviews, and such. And lots more. So I think for starters, the World Wide Web and internal information is quite enough. Okay, maybe I'll talk a little bit more about something that's an offshoot of intranet, in the sense that I've talked about intranet corresponding to commercial establishments. But if you think about it, the government also acquires enormous amounts of data. So if you talk to people in the government, most of them will tell you that they have a lot of data, but they don't know what to do with it. So one easy example is census data. It's not overtly textual, but they do have a lot of textual data as well. For example, if you look at a site called Juris, they have a digitized collection of various court judgments from all over the country. And to many of us, that may not seem like a terribly interesting collection of text. But for people connected with the legal profession, having access to the judgments delivered by courts all over the country over the last 50 or more years, that's a very valuable resource to have. So if you can properly utilize it, you get to see, in many cases, even those of us who are not particularly familiar with how the law works, for many of us, we know that kind of things get done by how they were done earlier. So if you have a precedent for a case, that's an argument in favor of how the case should be disposed. So having a history of 50 or more years worth of case histories, that's a very useful thing to have. But other than kind of general examples, the uniting feature of all of these is that, in contrast to databases, there's no overall structure that's easy to handle. So that's basically what leads to our the need for pre-processing. So the first task that we need to do is to take the natural language free-flowing text that does not fit into any particular structure and impose some kind of a structure on it that will make it easier to handle. So, so the first part that I'll be talking about, which consists of converting free-flowing natural language text to some kind of a structured representation. This is straight out of an information retrieval textbook. And the process is called indexing. So the idea is that any text item, so it could be a web page, it could be a judgment, as I said, any document is represented as a list of terms and associated weights. So these terms are basically keywords or content descriptors. If you read any technical paper, you know that a technical paper will have, apart from its abstract, a set of keywords telling you in very concise form what the broad area of the paper is. So think of the keywords here, T1 to Tn, as something similar. And the weight is a numerical quantity that's a measure of how important that term is in representing, or how strongly the term is related to the subject matter of the document. Traditionally, like I said, in a library setting, you would have people creating catalog entries for the index for a document would basically be a catalog entry. So you'd have kind of things like keywords corresponding to a item in the library. That's feasible because items in the library have a long production life. So whether it's a book or a journal article, it takes several months to get one ready. So manually assigning keywords to such an item, a process that would involve experts from a particular domain, that's feasible. But once you're working at web scale, kind of getting or expecting people to assign keywords manually to a web page, tell you what it's about, doesn't work. So basically what you need to do is you need a completely automatic method for building this construction or building this representation given a document D. So we'll break this into two parts. The first will take a document D and construct the list of keywords T1 to TA. And then we'll talk briefly about how you would go about, or how you might go about calculating the weights. So, given that we do not have access to kind of experts who are going to pick and choose certain keywords or content identifiers to assign to a document, your best bet is to rely on the words contained in the document itself. So you take a news article like this as an example. A human would say this is about cricket, about Indian cricket, about Sachin Tendulkar's retirement. But since we do not have the luxury of appealing to human experts like that, what we start with is simply a list of the words contained in the text itself. So from a algorithmic point of view, this is usually fairly straightforward. All you need to do is remember the input text is basically a sequence of characters. So all you need to do is look for things like white space and punctuation, which mark word boundaries, and you make a list of all the words contained in the input document. This is trivial for alphabetic languages, like most of the European languages, Indian languages. But if you're dealing with something like Chinese, which is an ideographic language, things aren't kind of broken up as clearly as it is in English into separate words separated by white space or punctuation. So how many kind of adjacent symbols make up a word, that itself is it is not as trivial as it is in the case of English or languages that most of us are familiar with. But I don't know any Chinese or Japanese, so I can't tell you very much about that. For the languages that we are dealing with, this is fairly straightforward. So from this kind of an article, you would start with a list like this. And you can already see that some of the words there, Sachin Tendulkar, is fairly strongly related to the subject matter of the document. But words like and but, any document at all that you write in English would probably contain these terms, and they have a predominantly grammatical function, not indicative of the content matter of the document. So from this kind of list of candidate words, the first thing that we need to do is eliminate all these words that have grammatical rather than semantic function. Well, semantic in the sense that they're not content bearing. So the words in red here, for example, could be candidates for deletion. The way this is usually done is you probably have for whatever language you want to process, you probably have a pre-constructed list of some few hundreds of words like this that are stop words. And sort of kind of going from this list to a refined list would simply be a list lookup step. kind of easily available on the net, standard stopword lists are easy to come by. But if you're exploring a new language, then this is something you'd have to construct from scratch. So one of the ways you might go about it is if you, and presumably you want to do something like this because you have a large collection of documents. If you have only a small collection, you can probably do it by hand. So if you have a large collection of documents, you might do something as simple as counting the frequency of all the words in that corpus. And usually the most frequent words would be words like this that have some kind of a grammatical function. So I mean, the algorithm, if you want to call it that, would be identify all the words in your collection, sort them in decreasing order of frequency, and maybe look at the top few hundred, like maybe 200 or 300, and refine it by hand. So you could actually have, because it's a purely automatic method, you might end up with some useful words in that list that just happen to be frequently occurring. So it's probably safe to take that list and refine it by hand. So once we have this list and we've thrown out things like and but, you're left with words that are to varying degrees related to the subject matter of the document. So the next thing we want to do is we want to do some kind of normalization. So this particular article is probably not a very good example of what I want to do. So it's sort of like, if you have, I mean, think of the words resignation, resign, resigns, all of them really have to do with the same general idea. So what we want to do is some kind of normalization which maps all of these to a common canonical representation. Similarly, analysis, analyze, analyzing, you might want to change it to a common representation. Notice that the common representation, depending on what you're going to do with it, need not be a valid English word. So the second example I've given is that you've changed all of this to analyze, which is kind of not a word by itself, not a valid word by itself, but depending on what kind of a processing you want to do, if you simply want to conflate analysis, analyze, and analyzing to the same feature, if you will, then this is kind of doesn't do any harm. So once again, for languages that have been studied for many years, standard algorithms are available. So the oldest algorithm, or one of the oldest algorithms that I know of, is one by Porter. So you can actually get code that implements a Porter stemmer freely on the web. So this mostly depends on grammatical rules. I mean, MF Porter, who wrote this algorithm, used kind of English grammar rules to determine what frequently occurring word endings are. Things like, I mean, ing is a frequently used word ending. So from running you go to run, from run you go to running. So things like ing, ed, es, these are frequently occurring suffixes. So you can look for those suffixes and chop them off. And then you might need to do some kind of small modification at the end of the word as well. So imagine having to do that for a new language. It kind of could be a slightly daunting task in the sense that you have to know the grammar of the language fairly well. So a little later, when we come to the actual text mining applications, I'll talk about some work that achieves the same end through techniques that are kind of more or closer to conventional mining. Okay, so what do we have so far? This is the list we started with. We've deleted all the non-content bearing words from it. And from what's left behind, we kind of, if things are variants of the same word, we map them to a common representation. So that's what we've achieved so far. If you think about it, then mapping things like resignation, resign, resigns to a common representation is one thing. But this does not take care of mapping things like automobile automobile, motor vehicle, and car to the same general idea. So something like a thesaurus might be useful for that purpose. So after all, you want to discover patterns like does a set of documents talk about air pollution caused by vehicles? So if some documents talk about motor cars causing pollution, others talk about automobiles causing pollution, you want to identify the fact that they're really talking about the same thing. So we're looking for some kind of normalization over and beyond what stemming gives to us. So the obvious kind of real-life analog or real-life resource that we use in such situations is the thesaurus. And it turns out this is somewhat difficult or maybe counterintuitive, but it's actually fairly difficult to use a thesaurus effectively if you're trying to do it completely automatically. And one of the reasons for that is words sometimes have multiple senses. It's the same word but means different things. So the kind of overworked example is bank. I mean, it could be a river bank. So that's the sense you'd want if you're talking about things like flooding and damage to river banks. If you're talking about commercial transactions, you're probably talking about the bank as a financial institution. So which sense of bank do you want to kind of, when you're looking up the thesaurus, which sense of bank? So that kind of presupposes that you have some means of finding out which sense of a particular word has been used in a given context. So that's not trivial. So far, so maybe what I'll do is, rather than talk about ways to effectively use a thesaurus later on, can you hear me at the back?
No.
Travel, right? Yeah. Okay, so basically because I have no easy answer to how thesauri can be used properly, we'll kind of leave it at that, but we'll revisit this later. Just like I said, we talk about a different way to stemming that has kind of stronger relationship with traditional mining techniques. We'll also look at something similar for how a thesaurus might be constructed automatically. But kind of that's about it for now. If you've been kind of following along, you've probably noticed that there's a difference between what I'm claiming to do and what you've seen in practice, which is to say, the examples I started with were keywords that are, I gave as an example keywords that are assigned to journal articles. So very often what you have, the keywords that you have are things like data mining, text mining, computer science. So those are really two words. It could be longer as well. So we've not done anything at all so far about capturing these multi-word keywords. So they aren't kind of single words. They have a function as a single keyword, but they're not single words. So in particular, the list of individual words that we started with at the beginning isn't going to give us things like computer science and data mining. So these multi-word terms, traditionally called phrases in the information retrieval literature, you could employ various methods to identify these phrases. One of them, like I talked about Porter stemming earlier, which is kind of linguistically motivated or linguistically based, you could have phrase identification methods which are also kind of determined by linguistic principles, in the sense that if you have a way to determine the parts of speech of a word, so you identify what's a noun, what's an adjective, what's a verb, and so forth, you might postulate a set of rules which says that two nouns side by side or three nouns side by side form a phrase. So things like computer science, data mining would fall into that category, computer architecture. Something like maybe even
an adjective followed by a noun, something of the kind. I mean, you could make up a list of rules like that. But once again, as with Porter's algorithm, that's language dependent. So it might be a better idea to use something that's more statistical in nature and therefore portable across languages. So when I talk about statistical methods, you could, and here I'm using a term that's traditionally used in a mining setting, you could try and measure the association between words. But something as simple as counting bigram frequencies, so what I mean is you again start with a large collection of documents, look at every pair of adjacent words, and you count the frequency of all such adjacent pairs. Any word pair that occurs side by side sufficiently frequently, you hypothesize that if they're occurring that frequently, then that's probably not a random event. So if that word pair has more than a certain minimum support, you call it a phrase. And I don't know of any experiments that conclusively show that kind of deeper language analysis consistently or reliably gives you better results. So some experiments, fairly old experiments, mid-90s I'd say, done with the statistical methods or the statistical method that I just talked about, which is simply bigram counting, and comparing that to linguistic methods like the kind I suggested earlier, actually showed that depending on what your application was,